Okay, so now we want to find the Taylor expansion, the second degree Taylor expansion of this function at the point 1, 1. And many of you might already be noticing something interesting, and I will explain it at the end of this problem. So remember that the formula T2 of xy, this is going to be f evaluated at 1, 1 plus the gradient of f. Remember, this is just the derivative, evaluated at 1, 1, dotted with x minus 1, y minus 1, plus 1/2 the Hessian of f, evaluated at 1, 1, times the vector x minus 1, y minus 1, and then we're going to dot this with x minus 1, y minus 1. I don't know if y'all can hear my son calling for me. I might have to pause in a moment and go down. Okay, so that's what it is. Now we just need to fill in all of this stuff. So let's first compute f of 1, 1. What is f of 1, 1? Well, I just plug in x and y are both equal to 1. So this is 1 plus 1 minus 1. So this is 1. The gradient of f, remember this is equal to fx, fy. We computed this in a previous example or a previous problem. So this is 2x minus y, and then this is going to be 2y minus x. And so the gradient of f, evaluated at 1, 1, okay, I had to pause it for a few minutes to go look at my son who just made a peanut butter jelly sandwich all by himself. I don't remember where I am, but I'm going to compute the gradient. Okay, so the x derivative, 2x minus y, x and y are both equal to 1. This is 1, and similarly, the y derivative is going to be equal to 1. Okay, and finally, we need to compute the Hessian. So let me remind you that the Hessian is equal to f. This component, it's a 2 by 2 matrix. This is the double x derivative. This is the xy derivative. This is the yx derivative, and this is the yy derivative. Okay, and remember, all this is the derivative of the gradient function. Okay, so the double x derivative, this is the x derivative, so the double x derivative is 2. The xy derivative, in other words, the y derivative of the x derivative is minus 1. I did not need to put a comma there, and I did not need to put that string mark there, but I did. This, again, the function satisfies Clairault's theorem, so we know that this is going to be minus 1, or alternatively, the y derivative, sorry, the x derivative, this is the y derivative, the x derivative of the y derivative is minus 1, and then the double y derivative is 2. Okay. So then, T2 of xy is, let me try to scroll up a little bit, is f of 1, 1, which is 1, plus the gradient of f, which is 1, comma 1, dotted with x minus 1, y minus 1, plus the Hessian 2 minus 1, minus 1, 2, times x minus 1, y minus 1. Dotted with x minus 1, y minus 1. Okay, and if we expand all of this, what do we get? So this is equal to 1 plus, if we do the dot product, this is x minus 1 plus y minus 1 plus, and I'm going to do this matrix vector multiplication, and then I'll do the dot product. And actually, I just remembered sorry, if you hear exasperation, it's because my son is now climbing into my lap. Plus, okay, we have the 1/2 there. Okay, and now I'm going to do this matrix vector multiplication and then do the dot product. So this is 1/2. When you do this matrix vector multiplication, this is 2 times x minus 1 minus y minus 1. And then this component here is minus x minus 1 plus 2 times y minus 1. And then we dot this with x minus 1, y minus 1. And then finally, what this gives us, this is 1 plus x minus 1 plus y minus 1 plus 1/2 times, okay, so the dot product of these two vectors, so this is 2 times x minus 1 squared minus y minus 1 x minus 1, and I'm running out of room, so I'm going to come down here, minus x minus 1 squared plus 2 times y minus 1 squared. Okay, and I just realized I made a mistake. I'm going to blame this on my son who's climbing in my lap. So this right here is minus minus y minus 1 times x minus 1. Okay, and so we can simplify this a little bit. This is 1 plus x minus 1 plus y minus 1. Okay, and then this is going to be plus y minus 1 times x minus 1 plus x minus 1 squared plus y minus 1 squared. Okay, and of course, one more mistake here. This should be a minus sign.
A minus sign?
Okay, sorry about those mistakes, but this now is the correct answer. And notice one way, let me write this next part in red. One way that you can verify this is if you expand everything out, then what you end up with is x squared plus y squared minus xy, which in this case is exactly what you started with. Now, why is that what we should expect? Well, we start with a second degree polynomial, and the second degree Taylor expansion gives you the best second degree approximation to the function. So of course, if you start with a second degree polynomial, the best second degree polynomial approximation is just that function. So what we've done is we've kind of taken the function as it's written, which we kind of think about being centered at 0, 0, though maybe that's not the exact right way to think about it. And we have now written it as if it were centered at 1, 1. Though what that exactly means is a little difficult. But one check, this only works for second degree functions. One check is just to see that you got back x squared plus y squared minus xy.